Yes, so thank you for the introduction. And on behalf of our team from the Institute of Automotive Technology from the TU Munich, today I want to present the multi-LiDAR localization and mapping pipeline that we developed throughout the last few months. So first I want to start with the motivation. LiDAR SLAM has been a topic for the last like 20 or 30 years. So why couldn't we just use some existing approaches? Well, what you can see on the bottom image here is our new research vehicle. We call it EDGAR. And this has a pretty unconventional sensor setup. So what most autonomous cars use is one 360-degree rotating LiDAR in the top of in the center of the rooftop. Due to the size of this vehicle, this was not possible for us because we would have had to lift it like 1 meter above the car. So we came up with a multi-LiDAR setup. And basically, we want to drive with the Autoware software stack, which does not include a mapping pipeline yet. So we also had to develop the whole mapping pipeline, not only for point cloud mapping, but also for semantic vector mapping, meaning we also need some kind of lane information to provide this for things like the path planning or the motion prediction of other vehicles. So the ultimate goal of our research is to have a scalable pipeline, because we also want to scale it to other places. We want to go driving autonomously all around Munich. So we do not want to have too many manual steps required for building maps. And we also need some kind of online localization and offline mapping. So I want to give a short recap of the related work, what has been done so far by other researchers. As I already said, there has been lots of research in the field of LiDAR SLAM and also in the field of multi-LiDAR SLAM. However, none of the existing approaches work for us because most of them have some kind of assumptions. For example, the rings that you typically see in those 360-degree LiDAR point clouds. So the best thing that was working for us was the KISS-ICP, quite new approach, and it's a great piece of code. So whoever wants to dive into LiDAR SLAM, it's great. So we built our work on this. On the other hand side, as I said already, we also need some kind of vector maps. The LaneLED2 is the format that is supported by the whole Autoware software stack. So we needed some kind of algorithms to create those maps. There are some approaches already. Most of them are deep learning based, which means they do work quite good on the data that we're trained on, but we do not have any capabilities for creating ground truth data. So we couldn't use them as they were just not generalizing to our data that we recorded with our vehicle. And also, like, they're super data dependent, meaning also they're lacking robustness. The last thing is whole mapping pipelines for building HD maps. Obviously, there's something in industry. However, this is not published, so we cannot really use it. And there is in research, there's no full pipeline published, so we hope we can pave the way for this. You can see an overview of the sensors of our research vehicle EDGAR. I put in the most relevant sensors for what we are doing right now. Also with, of course, cameras and radar sensors and so on. But for the approach I'm presenting today, the most important are the LiDARs. So we have two 360-degree Austral LiDARs that you can see in the front corners, left and right of the vehicle. They're tilted by 20 degrees. And they mainly cover the sides of the vehicle and also the short and mid range. For long range, we have two solid-state LiDARs by inversion to the front and the rear. And we also have an RTK-corrected GNSS receiver that gives us centimeter-level accuracy wherever the RTK correction and the GPS signal is there. So how does the map look like that we want to use? As I already said, we have some kind of circumstances. So it is a research vehicle. So we want to have an approach that is expandable. We want to have an approach that can be used with LiDAR maps, but also with camera maps. So we came up with this kind of multi-layer HD map. And each of the layers has like a different kind of appearance and also a different kind of downstream task. For example, one's for localization and another one might be for path planning. And the important thing is that they are all in the same coordinate system. I can translate, if I know my ego position in one of the layers, I can directly transform all of the information from the other layers. So this is what the pipeline looked like that we developed and that I want to present today. So you can see the two parts of it. The online localization part on top, which is basically pretty much a the standard LiDAR localization pipeline. We do some point cloud pre-processing, run filtering, voxelization, just handle the huge amounts of data in real time. Then we run point cloud registration. This was a really important part of the pipeline, and we needed this for the offline mapping, but also for the online localization, because in the beginning we didn't have perfect calibration, meaning the fusion of the point clouds of the individual LiDARs is quite difficult. And also this requires really precise synchronization, like time synchronization of all the sensors. And they are not triggered at the same time point, meaning there are some kind of differences. And just fusing all of the 4 LiDARs together into one single point cloud just didn't give us sufficient results. I'll show in the next slide how we handled this problem. And finally, everything comes together in a standard extended Kalman filter, where we also can use the GPS information, the wheel odometry, IMU sensors, and so on. The offline mapping is based on the same point cloud registration algorithms, basically. The important thing here is, as I said already, we based our work on KISS-ICP, meaning there is no GPS integration in this kind of SLAM so far. So we needed to do some kind of georeferencing. So in the mapping, we do have some kind of drift in the map we built and the actual world frame, so the GPS signal, for example, but to fuse them together in the EKF during the online localization, our point cloud map needs to be georeferenced. And it also needs to be georeferenced if we want, for example, to use some information from other sources. So what we use, for example, is the OpenStreetMaps to transfer information we don't have for our maps, for example, the number of lanes or the speed limits. So also this requires georeferencing. And this is the focus for today's presentation, basically the offline mapping, as it includes also more or less the relevant parts of the online localization. So as already said, the main challenges for us were the unconventional LiDAR setup. So we did not have running PTP time synchronization in the beginning. Also, the calibration was quite faulty. However, it somehow has to run in real time online. So what you can see on the right is the solution we came up with. So we did not fuse the point clouds of the LiDARs first, but we register each of the LiDARs individually against the map. What we can see here is the map that it's built, and it's a little bit shaking. And this shaking is exactly the wrong calibration for the sensors, because we have an initial guess for the position of each sensor, which comes from the calibration. But as there are errors in the calibration, the map tends to move. Next up is how do we get the semantic map information, meaning the lanes, and finally the lanelet 2 format. Once again, here we had some problems with our LiDAR setup, because we could not use existing approaches for 3D semantic segmentation on LiDAR point clouds, because also they were trained on 360-degree rotating LiDAR point clouds. So what we used, we semantically segmented the camera images, and then we transformed the segmentation levels onto the point clouds, which gave us a road segmentation of the 3D point cloud. Also, to make it a little bit more robust, we tried to detect the curves of the road sides and fused all the information together to get the lanelet 2 map. Next up is the georeferencing, and the georeferencing is also nice for the previous step, because it allows us to kind of use information from OpenStreetMaps and fuse it together, make some kind of assumptions, for example, where lanes have to be, so we can complete missing informations. How we did this, in the first step, it's a geometric alignment. So first we use the Umayama algorithm, which is quite well known in the field of localization and mapping. Just get a rigid, rough transformation between the actual GPS trajectory and our LiDAR SLAM trajectory. And then we use the rubber sheet algorithm, which uses some kind of control points. And we can either use the control points and set them manually in the user interface, or we can take them from the GPS when we have good GPS coverage. And this gives us a georeferenced point cloud map and also a georeferenced semantic map. And the last step, as already mentioned, is the map conflation, which does kind of an overlay between the map we just built and the OpenStreetMaps. This allows us to take features from there. So how well did this work? We do have a working pipeline. We can build maps, but there are some limitations, as you can see on the right-hand side with 2 images. On the on the top image, you can see the PCD point cloud of our campus that we built. And in the lower image, you can see the vector map overlaid with bird's eye view images, which shows that also the georeferencing is working. However, we do have some limitations. We are, with the level of automation, we are still not there yet where we want to be. There are still some manual refinements required. And one point, due to the separate registration of all the LiDARs, we're still struggling a little bit with runtime. So we are investigating how to further reduce the runtime of the online localization. This brings us to the outlook and the future work. As you have seen the shaking of the map before, this gives us information on the wrong calibration, meaning we can also use this kind of information to run online calibration of the LiDAR sensors, even if there is no overlap between them. Another huge point is more evaluation and enhancements to our approach based on this evaluation. We want to take our vehicle to different places all around Munich, all around Germany, and see how well it works, how well our algorithms generalize, and then do some kind of refinements. And one really important step is we have a project showcase at the Oktoberfest 2024, where we'll have an autonomous shuttle. So also there we have quite frequent map changes, as Munich throughout the Oktoberfest looks totally different from the rest of the year. This will bring us some more validation data, especially some kind of edge cases. So to conclude, I want to give a really short summary. We developed a localization and mapping pipeline for our research vehicle Edgar, which is kind of an unconventional LiDAR setup, meaning we need to develop better generalizing algorithms. We have online localization and offline mapping. The georeferencing was a huge problem there because at this point we don't have any GPS integration in the LiDAR SLAM we were using. We do have a working pipeline so far. However, there are still some more steps required to reach our final goal of getting a scalable localization and especially HD mapping pipeline. So part of our code is already online on GitHub. Check out the code, give us some feedback. And also if you have some questions after the conference, if you want to get in touch, you can contact me or my colleagues via LinkedIn. Thank you.